do this. Okay. So, logarithmic functions. We're going to be working basically the rest of this chapter is mostly about logarithms, but it's also about exponentials because logarithms and exponentials are inverse functions. One undoes the other, as we will see today in what we're doing. So a logarithmic function, is the inverse function of an exponential. Common logarithms are log base 10. If you see log, log, without a base number written, that is called the common log. That is log base 10. On your calculators do two logarithms. There are two types of logarithms your calculators do. Your calculators do log base 10 or common log. You see log, that's going to take the common logarithm. And when we use your calculators to solve the problems, we will use that one. The other one they do is what's called a natural log, which is what I actually do a lot of in calculus, and you'll work with it in pre-calc, where it's log base e. And you see ln, that's the natural logarithm. We just don't use that in here, but that is something I actually use more of later. Okay, but you'll actually see they work interchangeably when you're solving. It doesn't really matter which one. You'll get the same answer. Something that is really, really important to understand, and which we'll make for everything here today, is these two functions are the inverses. Log base b of x is equal to y is the inverse of b to the y power equals x. Logarithms in exponentials are inverse functions. You use one to solve the other. Okay, you use one to solve the other. We're going to go back and forth between those two things. This is really, really important to understand that relationship. What we're going to be doing today is we're going to be doing a lot of problems using the loop method, although we're not going to call it the loop method right off the bat. Basically taking logarithms, rewriting them as exponentials to be able to solve them. Okay, that's what we're going to do. We're going to take a logarithm, rewrite it as an exponential problem, and then solve them. And the entire rest of this chapter, and we only have 4 sections total in this chapter. Quick turnaround on this one, but it is an extremely difficult one. You have to have these rules and this process down big time. And it's all about solving logarithms using exponentials or solving exponentials using logarithms. Okay. We will solve some exponentials without logarithms, but there are some that you cannot solve without logarithms. Logarithms are good for a couple of things. The most useful thing is solving for an exponent. If I have an exponential problem where my variable is in the exponents, and I can't solve it in another easier fashion, which doesn't happen very often, I need to be able to use logarithms to solve them, and logarithms is the only way to solve them, and they're extremely useful for that. Probably one of the most useful tools with only one use. Okay. Now, logarithms are used for a few other things. Most notably that I can remember is in statistics, where you have data that isn't good. You can take the logarithm of all your data, and often it will make the data good, and you can work with the logarithms of the data and analyze that, then carry those conclusions over to the regular problem. Late bus? No, I said no, you don't need to pass. No, I said no. No. Late bus? You're just late. Okay. Not a problem. Okay, loop method is basically going back and forth between these two. That's what the loop method is. You take the logarithm, write it as an exponential, or take the exponential and write it as a logarithm to be able to solve the problem. That's what the loop method is. And that's most of what today is going to be doing, is doing that. Going back and forth between the two. Okay. So let's start. First one, convert to exponential form. Here's the trick. The base of my logarithm is the base of my exponents. So I have a log base 2 that means I'm going to have 2 to some power. That's the easy part. Once you get that down, so my logarithm base 2 means I'm going to have 2 to some power. And here's how you know what's what. You just swap which side of the things that are attached to. I have log base 2 of x is 3. That means 2 cubed is equal to x. That's what that is. This isn't that horribly difficult. If you remember, the base of my logarithm is the base of my exponential. That's the first thing. So I have log base 3 of 81 is x. That means 3 to the x is 81. We're not solving here. All we're doing is rewriting them. Log base 5 of 25 is x. 5 to the x is 25. Log base x of 49 is equal to 2. My base of my logarithm is x. The base of my exponential is also x. X squared equals 49. Like I said, we're not solving these. We're just rewriting them. Okay? Because those are inverse functions. 2 versions of the same equation. This works the same way in the opposite. I'm going to have a logarithm instead of an exponential. The base of my exponential is the base of my logarithm. So I have log base 3. Log base 3 of 81 is equal to x. Log base 2 of 64 is equal to x. Log base x of 27 is equal to 3. And then the last one here, log base 6 of x is equal to 2. Simple, but extremely important. Being able to go back and forth between these 2 versions is extremely important to be able to do. You can't do a lot of the work in here if you can't do this first step. You can't do today if you can't do this first step. Okay? So now it's your turn to try. So, once again, this is fairly simple. The base of your logarithm is the base of your exponent. 6 to the x is 36. X cubed is 27. 4 to the 0 is equal to x. And this one's the exact opposite. Log base 2 of 16 is equal to x. Log base x of 1 is equal to 4. And log base 5 of x equals 3.
Yes.
Yes.
So the 4 to the 0.
No, because we're not evaluating. Yes, we could solve these. So many of these problems you have the skills to solve now. What's, x equals 4 to the 0. What is anything to the 0 power? 1. So x equals 1. X cubed is equal to 27. Oh, x is 3. We can do that. We're not doing that right now. Our focus at this moment is strictly rewriting them. Strictly rewriting the problems. Okay? Because you've got to have that down first. Okay. Now, we're changing that. Okay, now here's the thing. There is something, and I keep forgetting to change. Every one of these is actually equal to x. Okay. And every year I say, oh, I'm going to go back and change them and make them all equal to x before I print them out. And every year I always forget. Maybe I'll change that. I don't know.
You're not going to do it.
No, because it makes life interesting. Ish.
It makes
So,
sense.
you can't Some of these, because I have done this enough, I can figure out what the answers are. But I've done this an awful lot. So for me, it's not that big a deal because I understand how logarithms and exponentials interchange. I look at the first problem, I go, okay, and in my head, I understand this means 6 to what power is equal to 6. And in my head, I can do that, so I can go straight to the answer. Please, you are not yet capable of doing that yet. And the only reason I can do this is because for the last few years, I've been teaching this, and I've got it down because I've been doing it over and over again. It's something that has to be fresh in your head. Your first step is to rewrite it. Rewrite the logarithm as an exponential, and then figure out what x equals. So 6 to what power is equal to 6? 1. Yeah. X equals 1. Rewrite it first. 2 to the x is equal to 8. So x equals 3. 2 cubed is 8. X is 3. 3 to the x is 27. X equals, 3 cubed. This one's a little harder. 5 to the x is equal to 1 over 25.
So it's 1.
Okay.
X equals -2.
X equals -2. 5 squared is 25. The negative makes it 1 over 25. X equals -2.
Good job, Dad.
What? No. Why is it -2? Okay, let's stop. Take a minute because we're actually going to work at doing this similar problem later. Okay. Think about, ignore the 5 to the x. Think about, I want to take this and write it as 5 to some power. Well, 1 over 25 is 1 over 5 squared, right? How do I get it out of the denominator? I move it up to the numerator and change the sign. This is where, when I said last chapter, you need to know your rules of exponents, this is the crap I was talking about. Because this is, if you had last chapter down, fine, this is a piece of cake. If you don't have last chapter down, this is a struggle, because that's what the negatives and positive exponents were about. You move it up to the numerator to get 1 over 25 to be 5 to the -2 power. So 5 to some power equals 5 to some power. That power is -2. That's what you're doing. And this is where, if you know your rules of exponents, and remember, when I have a fraction, that means I've got a negative exponent, it's easy to remember. Okay, last chapter is very important to what we're doing in this chapter, and that's one of the reasons why. You have to know your rules of exponents. So I get down to this one, I have 7 to the x is equal to 49. 7 to what power gives me 49? 2, so x is 2.
Yeah, good job.
11 to the x is equal to 1. 0, because anything to the 0 power except 0 is 1, so x equals 0. 10 to the x is 1,000. How many zeros do I have? 3. And then 4 to the x equals 64. X equals, what power of 4 gives me 64?
3.
3. 4 cubed is 64. And this is where knowing your perfect cubes and your perfect squares and things along those lines are extremely handy. But you can see what I'm talking about. Knowing your rules of exponents makes a huge difference to this one. Your turn. Do those. Okay, let's finish this. Okay, remember, quiet. Just like the previous page, these are all equal to x. because what we're trying to do is solve them. So I have 2 to the x equals 16. So x equals 4, 2 to the 4th power, 16. 2, 4, 8, 16. 3 to the x equals 64. And that's got, well, there is a solution to this problem. Not for a couple of days. We will learn how to solve this problem using logarithms in a couple of days. This is a typo. If it is, no, it's not 4, because 3 to the 4th is 81. 4 cubed, 4 cubed is 64. But where's my base? My base is log base 3. This is the correct looping. This is the correct way of writing it. We do not know, you do not yet possess the skills to figure out what x is with this number not being a power of 3. A whole power. It is solvable. You will get x as some decimal answer. Just do not possess the skills. This is a typo of a problem. So at this point, you can say no solution. That will end shortly. Okay. 2 to the x is equal to 1/8. Okay. 8 is 2 to the 3rd power because it's the denominator. X equals -3. 6 to the x is equal to 1, so x equals 0. 4 to the x equals 1/16. 16 is 4 squared, so I have 2, but it's in the denominator, so x is -2. And then 5 to the x equals 125. X is 3, because 5 cubed is 125. You should know your perfect cubes up through 5 cubed. You should have them memorized. It will make your life much simpler when we're doing these problems. Okay, this is the same thing we just did, except not all of them are going to be x by itself. You still have to rewrite it as an exponential, but the x isn't always going to be the exponent like the last set of problems we had. So this one, yeah, I hope you can get this one because we just did this problem. 5 to the x is 125, so x equals 3. The loop method, once again, is rewriting it as an exponential. That's your first step. So I have log base x of 5 is 1. That means x to the first is equal to 5. So x is what? 5. Because anything to the first power is itself. (27) to the 2/3 power is equal to x. Once again, this is a problem straight out of the last chapter. What's 27 to the 2/3? You have to figure it out. So the 3 in the denominator means cube root. Cube root of 27 is 3. The 2 in the denominator means I square that, which gives me 9. So x equals 9. I love it when something I've warned you about just comes to fruition so quickly and easily. It just makes me feel so good that I get to say I was right, see?
Wait a minute. Wouldn't it be 18? Why wouldn't it be 18?
What's 3 squared?
3 squared is 9.
Okay. The 3 in the denominator means I do what? I take the cube root.
Oh, okay, I get it.
There you go. See?
I understand.
See, if you paid attention last chapter, you would have got that one right.
I paid attention last chapter. This is every chapter.
Okay. So loop it, rewrite it, so you get 6 squared is equal to x. This one's easy, x is 36. Log base x of 3 is 1/2. That means x to the 1/2 power is 3. Okay, there are different ways of solving this problem. What does 1/2 power mean? Square root. 1/2 power is the square root. So this says the square root of x is 3.
It's 9.
So x equals 9. Because the square root of 9 is 3. Knowing what your exponents are really helps. 3 to the x is 27. What cubed gives me 23 to the third power gives me 27, 3 cubed. So x equals 3. Okay. Log base x of 1/64 is negative 3. X to the negative 3 is equal to 1/64. Okay. Well, the negative power doesn't really mean anything because it's already equal to 1 over something. So the negative gets taken care of there. What I need to do is, all right, x to what power equals 64? 4 cubed. So x is 4. 2 to the x is equal to 1 over 32. X equals, well, the 1 over means that it's going to be negative. And then 2 to what power is 32? 2, 4, 8, 16, 32. Doubling each time, I get 5, so it's negative 5. This one's almost the same thing. 2 to the x is equal to 1 over 16. So x equals negative, because I have 1 over, so it's got to be a negative power. Yeah, 2 to the 4th is 16. 2, 4, 8, 16. Four cubed equals x. This is easy. 4 cubed is 64. Log base 3 of 81 is x. 3 to the x is 81. 3 to what power is 81? 4th power. 3, 9, 27, 81. And then this one, log base x of 49 is 2, so that means x squared equals 49. So x equals 7. Because 7 squared is 49. Questions? Whose turn is it? Your turn. Okay. Let's do these. So log base x of 8 is 3. That means x cubed is equal to 8. Guys, focus, please. So I have x cubed equals 8. What number cubed is 8? It's 2. 4 to the negative 2 is equal to x. That's easy. Do 4 to the negative 2. That means it's 1 over 4 squared, or 1/16. This one's 3 to the x is equal to 1 over 27. X equals 1 over means that x is going to be negative. 3 to what power is 27? 3 cubed, so this is negative 3. X squared equals 121. What number squared is 121? 11, so x equals 11. 3 to the 5th is equal to x, 243. X equals 243.
Wait, how did you get to 43? Do you just
3, 9, 27, 81, 243. No, but that's what you're doing. You take 3 to the 5th power. That's what that is. So I had to pause because I'm like, oh, it's 243. I didn't remember. Pull that out of the memory banks. So this one is 2 to the x is equal to 64. 2 to what power? So 2, 4, 8, 16, 32, 64, 2 to the 6th. That's how I get my powers of 2. Start with 2 to the first 2, and then double it each time. Get 64. So x equals 6. X to the 1/2 is equal to 9. Square root of what is 9?
I mean,
Square root of 3 is not 9.
81.
Thank you.
We just snowed it yesterday.
Yeah, that's what the cold got to your brain. Is that it? Yeah. 8 to the negative 2 is X. Negative means it's 1 over 8 squared. 8 squared is 64. X equals 1 over 64. 36 to the 1/2 power is X. 1/2 power means square root. Square root of 36 is 6. Okay, X cubed is 1 over 64. Okay. This one's a little trickier, but it's not bad. I'm not going to have a negative. I'm not going to have a negative because although it's 1 over something, the power's not negative. I want to figure out, what number to that I cube itself, what number cubed gives me 64? Well, 1 over 64. So if I have a fraction, I'm essentially taking the cube root. This is going to be 1 over 4 because 1 cubed is 1, 4 cubed is 64. X to the negative 1 is 1 over 11. X equals 11. That's an easy one-ish. Yep. Nope. Next one, 27 to the 1/3 power is X. 1/2 is a square root. 1/3 power is a cube root. So the cube root of 27 is 3. Hey, there are a couple of rules of logarithms we need to talk about before going on. 1, you cannot take the logarithm of a negative number. The log of a negative number does not exist. You will not have log base 2 of negative 8. Log base 2 of something might equal negative 8, but you cannot take log base 2 of a negative number. Because, for example, if I have log base 2 of negative 8 equals some number x, that means 2 to the x equals negative 8. 2 times itself, no matter how many times, will never be negative 8. Because the only way to get a negative from multiplying is having one of your numbers be negative. And 2 is positive, and a positive times positive, no matter how many times, will never be negative. This is also why you're not allowed to take the logarithm of 0. The logarithm of 0 does not exist. You're trying to take the log of 0 on your calculator, it will say, nope, can't do that, dummy. You're not allowed to do that. That's what error means, by the way. Errors, calculator speak for dummy. You can't do that. Okay? Because nothing times itself will ever be 0, except for 0. So log base 10 of 0 doesn't exist because 10 times itself, no matter how many times you multiply 10 times itself, you'll never get 0. Okay, so you're not allowed to take logs of 0. You're not allowed to take logs of negative numbers. And by rule, the base of logarithms is always positive. Okay. Now, for those of you who were not here on Monday, missed the show, the notes are online too. You will notice that there is a new portion of your notes. Independent work. So after we get done talking about everything, you need to finish and do these problems as well. These will be checked when you turn your notes in at the end of the chapter. Okay, so you do need to have them down.